This first talk will be jointly done by myself, Tony Mroczkowski, and Matthias Reichert, who's at OHB and will introduce himself in a second. I am a millimeter submillimeter instrument scientist at ESO, and I've been following the AtLAST project pretty much since its start. So Matthias, do you want to say some things?
My name is Matthias Reichert. I'm working at OHB Digital Connect, which used to be MT Mechatronics a couple of years ago. So a company, designing and installing telescopes worldwide. During the AtLAST project, we were the industrial partner and basically spent most of our time with the actual telescope design that will be presented in this talk.
Thanks. Okay, so jumping in, we start with the basic landscape of submillimeter millimeter instruments across the world. So here we have mostly facilities that are limited in field of view to sort of 4 to 20 arc minutes. Typically, the larger dishes have smaller fields of view. And apart from a few small dedicated survey telescopes like the South Pole Telescope, CCAT, or now called FEAST, or the Simons Observatory, they tend to have small fields of view, and then these survey telescopes have very wide fields of view, but they're smaller, so lower resolution. Further, no existing large, and by large I mean greater than 15 meters diameter, aperture telescopes observed at higher than 350 gigahertz, nor are they in the southern hemisphere so far. So we define these AtLAST technical requirements basically at the very start of proposing for AtLAST design study. And they've evolved a little bit, but this is pretty much where we started and what we've been able to deliver with our design. So the basic wavelength coverage is similar to ALMA. It's 0.3 to 10 millimeters, so that's 30 gigahertz to 1 terahertz. We aim for a 50-meter diameter. This sets our resolution goals, or our resolution goals set the diameter, and also the collecting area defines the sensitivity. We aim for a very wide field of view. This is 500 times that of the LMT, essentially. We want 5 or more instruments so we can serve our wide ranges of science cases that have been defined and which Mark Booth will talk about next. We go for a classic Cassegrain Naismith optical design. We want to achieve 20 microns surface error in our nighttime observations in the best conditions. We aim for a typical mechanical pointing accuracy of 2.5 arc seconds. This will be improved through pointing models. So this is just the mechanical, so I wouldn't worry about it too much. Typical improvements are 5 to 10 times better than the mechanical pointing accuracy when you use a pointing model. We want solar observations. This is one of our many compelling science cases. We aim for a fast scan speed, fast acceleration, and elevation and azimuth limits that allow us to observe huge portions of the sky really easily. And then finally, we have a high sight so that we can actually see through the atmosphere. This next plot, so this isn't focused on the site selection or anything, but here I'm plotting the transmission curves versus the ruse efficiency for 20 microns and 30 micron half wavefront error. So the 20 micron is the solid one, the dashed one is the 30 micron half wavefront error, and basically see that the surface accuracy will not be the limiting factor for observations in typical conditions, versus median and top quartile conditions. So this is pretty much where we want to be. This is one of AtLAST's very salient features, aside from high surface accuracy and large collecting area, is its field of view. And when you combine the primary mirror diameter and the field of view, you end up with a throughput that is just transformatively large, basically 5 times larger than the best, highest throughput dishes in existence right now, and this is on a log plot. So, this is really where we want to be. This is what AtLAST is going to deliver. And this will allow us to be able to provide upgrades for generations and really deliver a facility that's upgradable, sustainable, and served many generations of astronomers after us. And we do this through a transformative optics design. So basically, we have very fast focal ratios. You know, the large collecting area goes to the secondary very quickly. You can see the rays converge very quickly. And then there's a folding tertiary mirror, and that's it. We only have three mirrors, so M1, M2, and M3, primary, secondary, and tertiary. And they go to the instruments, which are here. And the instruments are selected through M3, tilting around this axis. So that's easy to understand and look at and say, hey, you know, this is simple, versus having a lot of relay optics in many other instruments. So how do we do this? We looked to previous designs. This is a classic pintle bearing used by the LMT 50 meter, which was inspiration for a lot of things that we're doing here, but only goes up to 350 or 400 gigahertz. And we ruled that out quickly because it doesn't allow our large field of view. It doesn't allow the large receiver cabin that we aim for. And instead, we look to optical design. So the GMT and the ELT especially have this rocking chair design, and that's basically cradling the whole primary mirror. I think at this point, Matthias is supposed to take over with the designs. Yes. So this is where our CAD design is, and Matthias will take over for a few slides.
Yeah, thank you, Tony. So, as we don't have too much time, I will stick to a high-level description here of our design. So what you can see here on the left-hand side is the 90-degree elevation position of our current concept design for the telescope. On the right-hand side, you see the minimum elevation position of about 20 degrees. As Tony already mentioned, we have quite an impressive optic where we need to build a telescope around it. What we have is to start in the very top, a 12-meter secondary mirror, which is a carbon fiber structure due to weight reasons and stiffness reasons. You have a 50-meter primary mirror with an active surface. I will talk later about this in more detail. What we introduced, as Tony already mentioned on the slide before, is what we called an elevation wheel. So very similar to structure. Stop, Tony, not too fast. Yeah, maybe you can see it here on the right-hand side with the optical telescopes. So our design was inspired by the Giant Magellan telescope that we are currently designing here at OHB. And also the ELT that you can see here. This is an old picture of a study about 15 years ago. But this was our approach to somehow house the large optics that were developed in the project. Please go one slide. Yeah, thank you. No, that was one too far. Thank you. So you can see that the whole telescope is basically cladded, so you cannot see all the details. We will see that on the next slide. This is due to temperature control reasons. We need to have a sophisticated temperature control in the whole structure to avoid any large deformations of the steel structure that we intend to use. Over the high distances we have over the 50-meter reflector. And this is why we introduced this cladding comparable to LMT. You can also see that at the LMT telescope. So you do not see the main axis mechanics here in this picture, but you will see it on the next one. We have an apex shutter here in the apex to protect the tertiary mirror and also the instrument floors behind it. And we also introduced a couple of instrument and access portals to be able to exchange instruments and for any maintenance and service activities. Please also note here in this image the size of the telescope compared to a truck that we placed next to it. So we are talking about really massive dimensions. Please go to the next slide, Tony.
You have 5 minutes.
Okay, I'll hurry up. Here are some other pictures of the naked telescope, so without the cladding. This is still very conceptual images that you can see here. Maybe I concentrate a bit on the right side here. You can see the instruments that are placed around a tertiary mirror that is flat and then can rotate to guide the beam to one of the telescopes here. Please note that the red small telescope instruments, sorry, they do rotate with the elevation structure, while we have two large Nesmith instruments left and right. Oh, in this image here, up and upside on the upper and the bottom side, that are not rotating with elevation structure. So they are only rotating in the azimuth structure of the telescope. Okay, as I don't have too much time, please go to the next slide, Tony. We did a lot of FE modeling to investigate all the static load cases of the telescope. You can see here a couple of images of the actual FE model that we divided into the main structural parts. We did a lot of requirements flow down from the very basic requirements down to subsystem requirements and also to surface requirements, surface accuracy requirements. For the main reflector, for the passive main reflector, we derived a requirement of 200 microns RMS for the surface accuracy, while for the M2 surface accuracy, we derived below 10 micron RMS. And in both cases, we were able, for the static load cases, under gravitational load, to achieve those surface requirements. Please go one slide forward, Tony. We did the same for the active surface elements. So here you can see a very basic or simplified FE panel segment model that we introduced. It's basically inspired by the LMT, what you can see here on the left bottom side. The active surface of the main reflector is divided in about 400 panel segments that have actuators in each corner. And there we could also demonstrate that for the single surface panel, we can achieve the required surface accuracy. One slide forward, Tony. Thank you. One major challenge of this whole design is the metrology system. We somehow need to identify where are the actual optic elements and where are the panel segments in the current state of the telescope. And we investigated a couple of approaches that still need to be investigated in the next phase of the study. We investigated using so-called Etalon laser optical system that is used, for instance, at the FEAST telescope at the moment. We thought of using depth sensors on a thermal stable substructure, what you can see here in the middle. And we also had a look on wavefront control via microwave interferometer, as it was described by Tamura in the paper. One slide forward, Tony. Tony, okay, so back to you.
Okay, yeah, sorry, it took a moment for it to respond. Right, getting back to the optics experts among us here will note that probably 3 mirrors don't actually provide a flat diffraction limited field of view this way, or at least not our on-axis design the way it is. That is plotted here, that is addressed in Pato Gallardo's paper. Pato is shown here, and also here next to the ESO Large Aperture Telescope receiver, which is 2.4 meters in diameter for reference. And here he plotted the diffraction limited field of view as a function of wavelength. So it does get very tiny, actually, formally, as you go to higher and higher frequencies or shorter wavelengths. However, in his paper, he studied corrections to the optics, and these corrections are standard. They're being implemented in Simon's Observatory. They're planned for CNBS4, and they're in use in a number of instruments. So this is actually designed already, and he designed a way to break up the full field of view into an array of cameras and studied how, with corrective optics in the receivers, you would be able to recover. So this would be the native field of view. You would only recover this tiny bright yellow portion at each frequency. So this is 1.2 millimeters, 2 millimeters, 4 millimeters, and these are with the corrections. We should have an AtLAST forum from Pato in the future to tell us more about these corrections, of course. And then this is going to higher frequencies. You can recover still a huge portion of the field of view. And if you relax your straw ratio to 0.7, which is not formally diffraction limited, you can recover more of the field of view if you really need that. So that seems under control. Further, Roberto Pudu studied the physical optics of here. So we were concerned that the panel gaps and the struts would introduce polarization effects and beam effects that we didn't want. So this is the ideal case with no struts, no panel gaps, no surface RMS for reference. And this is the cross-polar beam for that same pattern. When you add the panel gaps of 3 to 5 millimeters, that hasn't been decided quite yet. It has essentially no effect on the beam. So that's where we want to be. And when you add the struts, it adds a small effect, but this is down 60 dB from the peak. So again, it's not really a concern. And then when you add the ruse scattering, that entirely dominates all of the response. So this is including the ruse scattering in addition to the struts and the gaps. And that's basically where we want to be. So the ability to accurately focus the surface is our primary limiting factor for both polarization and beam response. And that's also shown in this plot for the radially average beam. So again, we should discuss this further in a dedicated forum, but the optics look to be in good shape. So what's next? So we have AtLAST 2 happening, of course. This is our development project now, moving past the design study. From the perspective of the telescope design, we divided up what was formerly Work Package 2 and AtLAST to Work Package 2 being 2 packages. One focuses on the instrumentation and conceptual reviews of the telescope. Another one focuses more on the work at OHB, the design, the prototyping, the metrology, and overall engineering readiness. From my perspective, I'm running Work Package 2, and we want to translate our transformative science cases into firm instrument requirements and then proceed with designing these. And so these are the basic concepts that we have for the instruments. I won't go into it too much, but basically we have an array of things serving our various science cases. And from the continuum detective perspective, we're in a good heritage. Extrapolating up to nearly megapixel scales actually seems reasonable on the time scale of AtLAST. So this is all great. And then
maybe you can wrap up.
Yeah, so this is the last thing, is the Work Package 3 is the demonstration. So Matthias especially and his team will be focusing on the full system analyses that cover earthquake, wind, thermal, technology demonstrations. And in concert with APEX and Work Package 7, we're going to be testing the energy recovery system because there's a lot of energy spent in accelerating and decelerating the telescope. And in particular with deceleration, you can recover about 80% of that kinetic energy that's normally dissipated as heat and reuse it. So that's an environmentally friendly, forward-looking concept. So thanks.